This is part 11, fine-tuning, of the series, AI for Everyone. Why do we need fine-tuning? Fine-tuning is a crucial process in adapting pre-trained large language models, LLMs, to perform specific tasks or cater to particular domains. While LLMs are initially trained on vast and diverse datasets, they may not excel in specialized areas out of the box. Fine-tuning involves further training these models on targeted datasets, enabling them to generate more accurate and relevant outputs for specific applications. This process enhances the model's performance by aligning it more closely with the desired task or domain. Example: a technology company aims to enhance its customer support by deploying an AI that understands its specific products and services. They start with a pre-trained LLM like GPT-3 and fine-tune it using their customer interaction logs and product manuals. This fine-tuned model can now provide accurate and context-specific responses to customer inquiries, improving the overall support experience. So you may think, how is this different than training from scratch? Training an LLM from scratch entails building a model from the ground up using extensive datasets and computational resources. This approach is resource-intensive and time-consuming. In contrast, fine-tuning leverages an existing pre-trained model, modifying it with additional training on a smaller task-specific dataset. This method is more efficient, requiring fewer resources and less time, while still achieving high performance on specialized tasks. For example, if you are a bank, you can fine-tune on smaller set of data from banking domain, or if you are a hospital, you can fine-tune on medical data. If you saw the previous video on distillation in this series, you might think we were doing training in the distillation as well. So how is fine-tuning different in comparison to knowledge distillation? Knowledge distillation is a technique where a smaller model, student, learns to replicate the behavior of a larger, pre-trained model, teacher. The goal is to create a lightweight model that maintains performance levels comparable to the larger model, making it more suitable for deployment in environments with limited computational resources. While fine-tuning adapts a model to specific tasks, distillation focuses on compressing the model's knowledge into a smaller architecture. Fine-tuning does not require teacher model to run. Also, comparatively, distillation itself is more extensive and expensive to train, very close to original training, plus it uses data set that is huge in size, whereas fine-tuning generally involves training on fraction of data and is comparatively very lightweight and quick to run. There is another area where comparison between fine-tuning make more sense. It is known as in-context learning, or ICL. In ICL, we pass additional information that can be helpful to answer question in the prompt itself. In-context learning, ICL, allows LLMs to perform tasks by providing examples or additional information in prompt during inference, without modifying the model's parameters. The model generates outputs based on the context given in the prompt. While ICL is flexible and doesn't require additional training, it relies heavily on the quality and clarity of the prompts. ICL learning is temporary, and we need to provide all the data every time along with the question. This takes away or uses up the precious limited context window size, leaving lesser context size for question and answers. Fine-tuning, on the other hand, involves updating the model's parameters to internalize the desired behavior, leading to consistent performance without the need for detailed prompts each time. Fine-tuning may not be good for information that changes rapidly, as it will require that you again fine-tune to update the knowledge. As we learned that in-context window size are limited, a technique named RAG is utilized to optimize the usage of in-context learning. Retrieval Augmented Generation, RAG, is a framework that enhances LLMs by integrating external information retrieval mechanisms. In a RAG system, the model retrieves relevant documents or data from external sources based on the input query and uses this information to pass into ICL or prompt to generate more accurate and contextually relevant responses. This approach helps in grounding the model's outputs in up-to-date information, reducing inaccuracies and hallucinations. While this method helps optimize the ICL's context size utilization, it still requires to use ICL or prompt. In summary, fine-tuning is a vital technique for tailoring LLMs to specific tasks, offering a balance between performance and resource efficiency. Understanding its relationship with other methods like training from scratch, knowledge distillation, In-context learning, in frameworks like RAG, provides a comprehensive view of the strategies available for optimizing LLM performance in various applications. Default fine-tuning requires updating the weights and biases of all neurons, even when training on smaller datasets, due to the nature of backpropagation. However, backpropagation is a computationally expensive process. Engineers constantly seek ways to enhance the performance and efficiency of fine-tuning methods. This chart presents various options for optimizing the fine-tuning process. Our focus will be on LoRA, low-rank adaptation, a widely adopted fine-tuning technique that leverages parameter-efficient fine-tuning, PEFT, to improve efficiency. Low-rank adaptation, LoRA, is a technique designed to efficiently fine-tune large language models, LLMs, by significantly reducing the number of trainable parameters. Traditional fine-tuning methods require updating all the parameters of a pre-trained model, which can be computationally intensive and resource-demanding, especially for models with billions of parameters. LoRA addresses this challenge by introducing a more parameter-efficient approach. How LoRA works. In LoRA, instead of updating the entire weight matrix of each layer in the neural network, the approach focuses on injecting trainable low-rank matrices into each layer of the transformer architecture. These low-rank matrices approximate the changes needed for the specific task, allowing the original pre-trained weights to remain frozen. This method drastically reduces the number of parameters that need to be trained. For instance, applying LoRA to a model like GPT-3 can reduce the number of trainable parameters by up to 10,000 times, while still maintaining or even improving performance on downstream tasks. Let's take an example that does some rough calculation, as the exact number will depend on the training data set as well. For instance, training a 175 billion parameter model like GPT-3 from scratch would take approximately 36 years on 8 by 100 GPUs, or 7 months with 512 V100 GPUs. LoRA, by introducing low-rank matrices, the number of trainable parameters can be reduced by up to 10,000 times. For a 450 billion parameter model, this means fine-tuning approximately 45 million parameters. We could train the 45 million using 8 V100 GPUs, probably in 24 hours. Let us now dive deep into how LoRA is able to reduce the trainable parameters so drastically without affecting the performance of the LLM model. In short, think of LoRA as creating a too smaller matrix that, when multiplied, will result into original full parameter matrix. Here are the steps that we perform for LoRA. 1. We freeze the original matrix that has weights and biases so that it is not updated during fine-tuning. 2. We try to find linearly independent rows and columns within original frozen matrix. What this means is we try to find rows and columns that cannot be represented as dot product of two smaller matrix. This rows and columns will become our low-rank trainable matrix. Let's call it matrix A. The ones that can be represented as mathematical formula, usually by dot product multiplier, are stored separately as matrix B, called coefficients, to capture this multiplicity. The first two columns, C1 and C2, are linearly independent as they cannot be expressed into mathematical formula. So we mark them as linearly independent. The third column is linearly dependent, and linear dependency can be expressed using the formula C3 equals C1 plus 2 times C2. Fourth column is also linearly dependent, and linear dependency can be expressed using the formula C4 equals C1 plus C2. Fifth column is also linearly dependent, and linear dependency can be expressed using the formula C5 equals 2 times C1 plus C2. 3. Now we find the coefficient for the first row using values from just the linearly independent columns, which are C1 and C2. First row, first column R, 1C1, can be represented as 1 times C1 plus 0 times C2. So the coefficient will be 1 and 0. First row, second column, R1C2, can be represented as 0 times C1 plus 1 times C2. So the coefficient will be 0. And first row, third column, R1C3, can be represented as 1 times C1 plus 2 times C2. So the coefficient will be 1 and 2. First row, fourth column, R1C4, can be represented as 1 times C1 plus 1 times C2. So the coefficient will be 1 and 1. First row, fifth column, RR1 C5, can be represented as 2 times C1 plus 1 times C2. So the coefficient will be 2 and 1. This way we obtain another matrix, and let's call it matrix B. Now if you observe, the larger matrix can now be represented as dot product of two smaller matrices, A and B. 4. We inject matrix A in front of each layer of transformer. This is known as adapter, which will get trained during backpropagation, hence the name LoRa, which mean low rank adaptation. We obtain low rank and now using low rank as adapter. 5. Next, we fine-tune this low-rank matrix A, which will be considerably smaller than the original frozen matrix. 6. Once we complete our fine-tuning, we can recover full matrix by applying the dot product multiplication with low-rank matrix A to matrix B. 7. Since our fine-tuned model is now of the same size as original frozen model, we rehydrated or unfreeze our frozen matrix and add up the weight and bias from fine-tuned matrix back to the original matrix, thereby transferring the fine-tuned knowledge back to original matrix. Here are some very rough calculations to show how different ranking affects how many parameters you will have to train. Rank of 8 should be good one to start with, and you may increase up to 16 or more. The larger value will keep it close to the original performance level. Here is a chart that compare the performance between full fine-tuning versus various other fine-tuning technique, including LoRa. As can be seen in the chart, LoRa not only performs best in the benchmark, but also beats the full fine-tuning. Now LoRa reduces the parameters that we want to train, but we can take it further and use quantization. Remember, from our previous videos, in quantization, we use lower precision data type like INT8 or FP8, thereby further speeding up the calculation. That is what quantized LoRa does. There are few variants of LoRa as shown in the picture. Hi, I'm Naunihal Singh Sidhu, a Microsoft Certified Azure Solutions Architect with over 25 years of experience in IT, specializing in AI-driven transformation, enterprise architecture, big data solutions, and digital innovation.